So, there we go. Alright, so number one. How long does it take for an echo to return to you up a cliff that is 185 meters away? So, I would start off with, let's see. I'd start off with something in the Y like the sound must go there and back, and then continue on with the speed does not change since medium does not change. Not change. And then pulling equations from my equation sheet, I would pull D equals, let's see, let's get to the equation. And this is back to first day, D equals D naught plus V delta T. So, and let's see, if it's got to go there and back, it's 185 meters, so the distance traveled will be 2 times 185 meters equals, we'll put in 0 here, plus 343 meters per second, so that's the speed of sound, delta T, solve for delta T, and you're all done. Tricky. Yay! Alright, number 5. What noise? I don't hear any noise. Anybody else hear a noise? No, I don't hear anything. Maybe it's in your head, Sam. Alright, pedestrian is waiting for lights to change in a second to hear a car approaching with its horn blaring. The car's horn produces a sound with the frequency of this. How about the pedestrian hears the frequency of this? Ah! Good old Doppler effect, Doppler shift. Number 4. Let's use green. The sound frequency and wavelength are changed due to motion of, hello, Mr. Cochran. Yes. All right, thanks. Bye. Claire, you are dismissed. Motion of car, otherwise known as the Doppler effect. Moving towards gives higher frequency. So I'm going to grab my equation because I don't feel like rewriting it. So we get down here to our wave stuff and down to our Doppler shift equation. And I thought I'd open that. I guess I didn't. Let me grab that.
Can I use your calculator?
No, I'm going to need my calculator.
Oh.
Sorry, I'm in the middle of. So, we need to pick this. Let's see, I think we're told some of these. Let's see what we're told. We're told that produces a sound at 381 and the pedestrian here is 386. So this is 381. The perceived sound is 386 hertz. So what does that mean about the fraction in those parentheses? Bigger than 1 or less than 1?
Bigger.
Bigger than 1. It's got to be bigger than 1, right? And now, which one's moving, the observer or the source? Is the thing hearing the sound moving or the thing making the sound?
Making.
Making. So the source. So I'm going to cross off the observer because they're not moving. It's 0. So now I've got B sound over the speed of sound plus or minus the speed of the source. I need a number bigger than 1. How am I going to do that? Do I need a bigger number on the top of the fraction or the bottom of the fraction? Top. So I'm going to use a negative in here because that'll make my fraction greater than 1. Yes? Does that make sense? That's the logic to use. You know, if they're getting closer together, inside the brackets has to be bigger than 1. So use plus or minus depending upon which way you want to do it. If they're going apart, inside the fraction has to be smaller than 1. And so pick the other one. It's the easiest way to remember it, I find. So what I care about, so I'm going to write this again. 286 hertz equals 381 hertz, brackets, speed of sound over speed of sound minus the speed of the car. Now, do I know the speed of sound? Yeah, 343 meters per second. So really all I have is the speed of car that I don't know. But let's do a little bit of the algebra. All right? Because what do I have to do to get that off the bottom of the fraction? How do I get that up top? Cross multiply, right? You got to bring it across and up.
Yeah.
So I'm going to have 386 hertz multiplied by that V sound minus V car. That's going to equal 381 hertz. And the only thing I have left over here is V sound. Oh, I can divide both sides by the 386 hertz, right?
Yes.
So now I'm just trying to isolate now, right? Think you can do the rest?
Yeah.
Now remember, V sound, actually I'm going to do one more step. 343 meters per second minus VC equals 381 hertz. 343 meters per second over 386 hertz. And then just a little bit more algebra and you've got it. All right?
Yeah.
You guys need a moment to work on that one? All right, so on to number 2, where you've got the pop bottle. We can tell this was written by a Midwesterner, pop, rather than soda, or
Oh, yeah.
if it was written in the South, it would be a Coke bottle. Well, that was one of those things I had to get used to when I went to Georgia Tech. Everything's Coke.
But you go to Texas.
Yes, yes, for a Coke. I said, okay, you know, what do you want? Oh, Sprite, you know, root beer. The Coke is headquarters there.
If you want an actual Coke.
Then you say, can I get a Coke? Yeah. Okay, what do you want? Oh, Coke. Okay. Weirdest thing to get used to. But, all right. So we've got, would this bottle be acting like an open or a closed pipe? Closed. Remember, closed is only closed on one side. If we close it on both, we get nothing. So it's a closed pipe, which means if I draw what it looks like, if I draw the pipe, looks like that, with the wave inside of it, only at the fundamental, we go from antinode to node, and so we have a quarter of a wavelength inside the closed pipe at the fundamental. That's the smallest bit of the wavelength that will fit in there. And that's kind of what I put for my Y. You know, bottle acts as closed tube. So node at water and antinode. That must be Friday. At top. And that leads, so right away I can write, well, L therefore equals 1/4 lambda. Right?
Yeah.
And now maybe I should look and see what do they actually ask me for. The bottle is 26 centimeters tall. The height of the water is 8 centimeters. Treat the bottle as a pipe that is closed at one end. Oh, wow, as they told me. And open at the other. So, 26 centimeters tall. And then my water is 8 centimeters deep. That means that, so if I draw my little diagrams, I've got what, 26 was it? 26. And then I've got 8 here, and then this is L. So my L is 26 minus 8, and both those are centimeters, which gives me 0.18 meters. Right? What tricky thing did I just do? I was just very tricky.
Oh crap, I thought that was 28.
I think it's 26 and 8, right?
Yeah.
Come on. Alright, no tricky then. I can just use V equals lambda F. I know my speed, 343 meters per second, because it's a sound wave. Lambda is going to be the wavelength. So if that's my L, that means lambda equals 4 times L from here, right? So that's 4 times 0.18 meters, or 0.72 meters, and then F. And then I just solve for F. And I'll get an answer in hertz, since I'm in meters per second and meters. When I divide meters per second by meters, I get 1/seconds, which is a hertz. Yay! All right, so we're doing number 9 here. String tied to wall at either end. The wavelength of the first harmonic of this string is 0.6 meters. What is the separation between the walls? I don't even think I need to do any math on this one. Let's just do the drawing. So I've got a wall, and then I have my string at the first harmonic, or what's also known as the fundamental frequency, would look like this, right?
Yeah.
Right?
Yeah.
So L equals half a wavelength, right? If you think about this continued on, there's a full wavelength, only half of it's fitting between there. They told me the wavelength of the first harmonic string is 0.6. So, 1/2 times 0.6 equals 0.3 meters. All right? You're welcome. I wonder if that's right. Seems too simple. Doesn't it?
So we talk about illustrating.
Oh, I required units on this one? Yay! All right, so number 10. Standing wave, 603 hertz, is produced on a string 4 meters long and fixed at both ends. So that right away we know that it goes node to node. And then they tell me the speed, how many antinodes will be in the standing wave. So I know that it has to be in chunks of half of a wavelength. So what I'm picturing here is my string looking something like this with some, I don't know how many of them are there. But I know that this has to be like some multiple of lambda over 2, because each of these is lambda over 2. And I have to go that node to node. So it's going to be some multiple of lambda over 2. What multiple, I don't know. What I'm going to do is I'm going to figure out the wavelength using V equals lambda F. They told me my V, for me it's 603. I don't know lambda, but F they told me, 600, they made my life nice. Because I can do that math in my head, right? What times 603 equals 603? So my lambda is 1.00 meters. So in my 4 meter long string, they want to know how many antinodes are there in the standing wave. So I've got 4 meters here. I'm going to do it through drawing because otherwise I think I'll confuse myself. Now I'm going to break that into as many meter long pieces as I can. So I can break it into 4. And within that, each of those is a full wavelength. Not a great drawing by me. But within each one of these 1 meters is a full wavelength. And they want to know how many antinodes. So let's see, that'd be 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 antinodes in mine, because there's 2 for every wavelength. And I can put 4 wavelengths in there, and so my answer must be 8. See if it is. Units? No units. Yay!